Welcome to a deep dive into, well, one of science's really big revolutions.
Mm.
For ages, physics wrestled with this concept, the luminiferous ether, this invisible stuff supposedly carrying light waves. But what if it was just wrong?
That's exactly what we're exploring today. We're digging into notes and papers from a 1920 University of Calcutta publication. It's actually where Einstein's and Minkowski's original relativity papers first hit English, our goal. To see how some really weird experimental results just dismantled that whole ether idea and how that led to a totally new way of thinking about space, time, even matter. So yeah, get ready. This might stretch your understanding of reality a bit.
Okay, so this ether idea, an invisible medium for light. I mean, it sounds pretty reasonable on the surface, doesn't it? Like sound needing air or water. So what first started to poke holes in that neat picture?
You're right. It felt very intuitive back in the 19th century. But the universe wasn't quite cooperating, even early on, like 1819 with Arago's prism work, and then Ari Boscovich in 1871. They kept getting these null results. Basically, things happening with light in moving stuff like water seemed totally unaffected by how fast that stuff was moving relative to this fixed ether, which was weird.
Yeah, that doesn't quite fit, does it? How could the medium not matter? So how do they try to, salvage the theory?
Well, they got clever. Fresnel, for instance, he came up with this convection coefficient. The idea was maybe only part of the ether gets dragged along by moving things, like just the excess bit. And Fizeau's experiment in 1851 with flowing water actually seemed to confirm it. It measured that exact coefficient.
Ah, okay. So for a moment there, it looked like the ether might just about survive. A bit patched up, but still there.
Exactly. It sort of limped on for a while. But the fundamental problems,
Yeah.
they were still there. And then came the big one, the real turning point our sources point to, Michelson-Morley, 1881. What were they trying to achieve?
Right, this is the famous one. They wanted to nail down Earth's motion through the ether, right, by comparing light speed parallel and perpendicular to our orbit.
Precisely. Think of it like swimming in a river. It takes longer to swim upstream and back than across and back, same distance. Light should have shown that difference if it was moving through an ether wind.
Makes sense.
Yeah.
So what did they find?
Well, here's the kicker. A definitive null result. Nothing. Both light beams took exactly the same time. No difference whatsoever. No sign of Earth moving through any ether.
Wow. Not just a small effect, but nothing. That must have caused some serious headaches.
Oh, absolutely. It was a massive blow. And other experiments started piling on. Lodge in 1893 showed there wasn't any kind of ether drag or viscosity from moving objects. The whole ether concept, as our sources put it, had kind of outgrown its usefulness. It got too complicated, too arbitrary. Plus, experiments with electricity and moving materials just weren't matching the ether predictions.
So the ether's crumbling. And people like Fitzgerald and Lorentz tried to explain the Michelson-Morley result away, contraction, and this local time idea. But they saw them as mathematical tricks, almost.
Yeah, sort of mathematical fudges to make the equations work. But then came Einstein in 1905, special relativity. He didn't just see tricks, he saw physics. He proposed two earth-shattering principles. One, physical laws are the same for everyone, no matter their constant speed.
Yeah.
Two, the speed of light is constant, always, for everyone.
And that just dissolved the ether, made it unnecessary.
Completely. Suddenly, space and time weren't fixed things. They were relative to you, to your motion.
Yeah.
Minkowski then wove this into the whole four-dimensional space-time idea, a unified reality.
So it means the time you experience, the distances you measure, it all depends on how you're moving. That's quite a thought. And the experiments backed this up.
They did. Experiments showed electron mass actually changes with velocity, just like relativity predicted. That Lorentz-Fitzgerald contraction wasn't just math anymore. It was a real consequence of this new relative space-time. The ether was entirely superfluous.
And Einstein didn't stop there. 1915 general relativity, taking it to accelerated motion. Gravity isn't a force, but the shape of space-time itself.
That's the leap. As Eddington famously put it, matter doesn't cause the curvature, it is the curvature. Or maybe it's the presence of matter that is the curvature. And this explained things Newtonian physics couldn't, like the weird wobble in Mercury's orbit.
Right, the perihelion advance and the famous confirmation.
The 1919 solar eclipse. Watching starlight bend around the sun exactly as predicted by space-time curvature. A huge validation.
Amazing. So what started as experiments just refusing to fit the mold, it forced this incredible shift in thinking.
Yeah, we went from this invisible fixed background jelly, the ether, to seeing space, time, and matter as this single dynamic thing. Gravity literally is the bending of that fabric.
a total paradigm shift
Sure.
from fixed stage to dynamic player. And it's interesting, our source material mentions that even with all this unification, electric force was still seen as a kind of outstanding peculiarity, not quite folded in yet.
Right, which leaves us with a really interesting question, doesn't it? What other things that we currently see as totally separate, like fundamental forces maybe, might eventually turn out to be just different aspects of one even deeper, simpler reality, something for you to think about?